today, rather than deriving some stuff, I thought I'd walk you through the Python code that computes the element residual and tangent for the model problem for the quadrilateral element. So I just uploaded this Python notebook. And if you recall the weak form for the model problem, which is basically like a heat transfer problem, it has a diffusion term and a source term. And the weak form has this integral in it. So the integral over the element of the flux times the gradient of the shape functions, or the weighting function, sorry, plus the integral of the source term times the weighting functions. And then the flux term is given, it depends on theta, possibly. It definitely is depends on the gradient of theta, and then the conductivity might depend on theta, and then the source term might be some nonlinear function of theta as well, for example. And the W is the weighting function. So if you plug in the discretization for the weighting function, that is W equals sum of shape functions times the nodal values of the weight function, and you rearrange things such that you take out the nodal values of the weighting functions, then you can get an expression where you have a vector with the nodal values of the weight function multiplying a vector, which is what we call the residual. So again, if you have W, maybe I should have put it here, W equals sum of shape functions times nodal values of the weight function. You plug that here, and then you leave the shape functions inside of the integral, but you can take out the nodal values of the weighting function, so they end up here in this vector. And then whatever you have to multiply that with, that's going to be your residual. In this case, the residual will look something like this. Note that it looks kind of similar. So you have integral of over the domain of the element. The flux stays there. The thing that changed is that before you had gradient of shape functions, now you have the gradient of the basis functions, and you have, or shape functions, and you have 4 of them, right? So the subscript A could be, 1, 2, 3, or 4. So again, just change the, when we introduce W equals sum of shape functions times nodal values, and we take the nodal values of the weight function out, then you end up with just the shape functions here. So shape function A. And then in the other term, you get, again, integral of the source term that stays the same, but now instead of W, you only get shape function A. And again, this has 4 components because there's 4 shape functions for the quadrilateral element. This is only true for the quadrilateral element. And then for this example, consider the K, the conductivity is just theta, for example, and the source term is just this function. These are just some random functions to illustrate the point. The shape functions and derivatives of the shape functions for the quadrilateral element are defined with respect to the parent domain, the one in psi eta space. So from -1 to 1 in this space. And I have just one element, again, like some random element with 4 nodes, and it has 4 values for the field theta. And I'm just plotting it so that you can see more or less what the shape is and how the theta field changes in this quadrilateral. But that's about it. So we have to compute the residual. Now the residual involves integrals, right? So if you look back again at the residual, it involves taking integrals. We have talked about this before. We're going to do numerical integrals, so Gauss quadrature, and then you can look this up for the quadrilateral element. We need points in the psi eta space. I'm going to do the 2x2 Gauss quadrature rule, so a total of 4 points. These are the 4 points, and these are the corresponding weights. I will initialize the residual, and then I have a loop over the integration points. This is a loop over the integration points. In this loop, I basically read in the value of the psi and eta for that integration point, and then the value of the weight. I evaluate the isoparametric map. So the shape functions are defined in terms of psi and eta. The functions are defined above. So I evaluate them at the corresponding integration point. And then using the value of the shape functions at that integration point, I can compute the corresponding value of x. I can also compute the Jacobian, which is the first I need the derivatives of the shape functions, again with respect to the xi space. So I already have defined the functions somewhere above, and I'm just calling the function here. So I evaluate the derivative of shape functions with respect to xi eta at the xi eta of the integration point. With that, I can compute the Jacobian. This dx dxi is the Jacobian. This is going to be a 2 by 2 matrix, which is basically the derivative of the isoparametric map. And this is in the notes. So this is the sum of the outer products of the nodal coordinates times the gradient of the shape functions with respect to xi. So x1e times dn, this is the gradient of the first shape function with respect to xi, and so on for the other nodes. So that's the Jacobian. I need the inverse transpose of that, so I just get that. And then with the inverse transpose of the Jacobian, I can get gradients of shape functions with respect to x, right? And that's just the multiplication of the inverse transpose of the Jacobian times the gradient of the shape functions with respect to xi gives me now the gradient of the shape functions with respect to x at this integration point. I can evaluate now. I have also, I'll need to interpolate the theta field. So again, just use similar to the isoparametric map, but instead of interpolating geometry, we're just interpolating some field. So shape functions times nodal values gives me the value of theta. I also maybe need to evaluate, I actually do need to evaluate the gradient of theta, and that one is again just nodal values times gradients of shape functions with respect to x, because what I want is the gradient of theta with respect to x. So that's why I have here. And note that this is why I needed to compute these derivatives of the shape functions with respect to x that I have here. Finally, I need a conductivity, which is some function of theta. So note that this is a function of theta, and theta is being calculated now at the integration point, right? And the same for the source. The source is a function of theta, and I'm evaluating it at the integration point, because this theta is basically the theta at the integration point. And finally, just integrate the residual. So that's just, you have to continue adding to the sum. So that's why I have this plus equal the weight of the integration point times the determinant of the Jacobian times whatever is inside of the integral. So if you just go back briefly, what is inside of the integral is q dotted with the gradient of the shape function a, and that will be like 1, 2, 3, 4, or in this case 0, 1, 2, 3, plus, and then forget a little bit about the integral, just look at what's inside of the integral, s times na. And that's exactly what I have here. So k times the dot product of the gradient of theta times the gradient of the shape function. And then, as I said, each shape function corresponds to one entry of the residual, plus s times the shape function. And again, shape function can take values. Above I have a equals 1, 2, 3, 4, but because of Python numbering, it's 0, 1, 2, 3 here. So that's it. That's how you integrate the residual. So we get a vector that has 4 entries. So hopefully that made sense. And then for the tangent. So for the tangent, what you need to do first, and I did this in the videos on Tuesday, is you linearize the residual with respect to the increment, to some increment of the field, theta. But then, after you do the linearization, if you plug in the fact that the increment is also discretized, and in the same way that the theta field is discretized, so sum of shape functions times nodal values for the increment, then what you can do is that you can leave the shape functions inside of the linearization and just take out the nodal values of the increment. So if you do that, what you will end up will be with a matrix dotted with a vector which has the nodal values of the increment. So this delta theta IE. Again, do let the linearization with respect to some random increment delta theta. But then when you plug in this definition for the increment, you can take out the nodal values of the increment, and then you end up with a matrix. In this case, because we have 4 nodes, so this will introduce 4 shape functions. When we plug out these nodal values of the increment, we end up with a 4x4 matrix that looks like this. So it has entries A, B. I should note here A again equals 1, 2, 3, 4, and B equals 1, 2, 3, 4. So we have 4x4 combinations. And I'm not doing the linearization carefully here, but if you go back to the video from Tuesday, the linearization, for example, for the flux term, you need derivative of the conductivity with respect to theta, and then you end up with the shape function, because this would have been derivative of k with respect to theta, increment of theta. But when we put in the increment of theta as the sum of shape functions times increments, and we take out the increments, we end up with basically just the shape function, but now index b, times gradient of theta times the gradient of shape function a, which we had before from the residual. So that comes from linearizing the conductivity term. If you linearize the gradient of theta term, you end up with conductivity now times gradient of, and now instead of having gradient of the increment, which is what you would get by linearizing the gradient of theta, you would get the gradient of the increment. But once you plug in this discretization of the increment and you take out the nodal values, all you are left with is gradient of shape function b. So gradient of shape function b times gradient of shape function a, which we had from before. And then this is the linearization of the source term. It's just derivative of the source term with respect to theta times linearization, which would be just this increment. But again, once you plug in the discretization of the increment and you take the nodal value out, you end up with just the shape function. So shape function b times shape function a. That one, the a is from before, the b is the new one. And that's about it. So this is, again, the linearization. Note that there's a and b components, so there's going to be shape functions a and b inside of this. Again, to integrate numerically, 4 integration points with their corresponding weights. All of this is the same up to this point as we had before. Now I also need the derivative of k with respect to theta, derivative of s with respect to theta. And in this case, I'm just going to do it within 2 for loops. So in the residual, I actually had, residual 0, 1, 2, 3, 4. Here, I mean, you can see that the definition is pretty good for for loops, right? So components a, b, and then I have, a and b here for the shape function that I need. So I just basically copy what I had, like this definition, and you will see. So I have weight of the integration point, determinant of the Jacobian times, and here you can see this term right here comes from the linearization of the conductivity. So dk d theta times, and instead of the increment, you end up with just the basis functions b, and b will take values 1, 2, 3, well 0, 1, 2, 3. This term remained the same, so dot product of gradient of theta times gradient of shape function a. This one it was from before. Then if you linearize the gradient of theta, you end up with now the conductivity stays the same, but now the linearization of the gradient of theta basically ends up with the gradient of the shape function b times gradient of shape function a. And finally, linearization of the source term, you have ds d theta times, and you will need here the increment, but the only thing that you get is actually the shape function b. And again, the shape function a is what we had from before. And that's it. So after you compute these 2 for loops and this outer for loop, which is over the integration point, then you get your tangent. So that's what I wanted to do today. I uploaded this notebook. And so, yeah, basically this has a way of computing the residual and the tangent for the model problem. And I think that's all I'm going to do for today. And on Tuesday, we are finally going to do the solution. So now we have the residual and the tangent. Now we can, for a single element on Tuesday, my plan is to basically just solve a simple example, but solve it with a finite element method for, a 2D problem of heat transfer. So that's my goal for Tuesday.